Hi, I'm Natalia, and today I'm going to talk about the SimVascular Python API application programming interface. This is a tool that allows a user to access the function of SimVascular from Python without having to manually interact with the GUI, the graphical user interface. And so this is a really helpful tool for automating workflows that use SimVascular functionality. The first place to go for help with the Python API is the documentation. That can be found on the SimVascular website under documentation at this Python interface link. And here you can read all about the Python interface and all the modules and functionality that it supports. You access the Python interface by pointing to your installation of SimVascular and then adding this Python suffix behind it to call the installation of Python that was installed along with your SimVascular installation. So if I do that, I'll be able to do import SV, which is import SimVascular, and now I should have access to all the SimVascular Python API modules, for example, sv.geometry. And something you can do from here always is help SV, and you can also ask for help with specific modules as well. So this is a useful thing. Most of the time, though, when you're trying to automate a workflow, you'll write a script first, and then you'll just execute that script using SimVascular Python. So let's go ahead and look at that. I've prepared a little example script for us to use today here. And in this one, we're going to build a vessel with a stenosis from scratch and generate the meshes that we would need to run a simulation on it, a fluid simulation. So the first thing you need to do is import SimVascular, of course. And then I've just created this folder results to which I'm going to save all the files that we generate in the script. Okay, so now we can move on to the workflow that's really similar to what you would go through if you were going to do this in SimVascular. So first, you need to decide on a set of points that are going to define the center line of the vessel. And here I've just chosen 5 points going down the x-axis. Then you need to create a SimVascular path object and set these locations that you chose as the control points. And from there, you can also extract these curve points, which are basically the points that describe the curve of the SimVascular path object. So these are determined based on the control points that you inputted earlier. And at this point, you can already go ahead and save this path. So let's go ahead and just run the script up to here, and then we can take a look at the path in SimVascular. So I'll delete everything that's here now, and we'll create everything fresh. All right. Okay, so I'm pointing to my SimVascular Python and then my script. Here we go. Great, so now we've executed up to this first breakpoint, and we've generated our results folder, and now we have this path object here. So we can go ahead and take it into SimVascular, and we can see that indeed we do have these 5 control points and a path between them. So that's great. The next step is to define the vessel lumen along the path. Since we want to have this stenosis, I've made the radius 0.5 everywhere except for in the middle where we're going to have the narrowing, and there I have it at 0.3. So now I need to generate a contour for each one of these control points using each one of these radii. So the way I'm doing that is I'm just looping over these original locations I provided. And then for each one of those, I'm making a contour object, which is a SimVascular Python segmentation.circle object. For that, I need to define a radius, which I'm getting from here, a center, which comes from these locations, and a normal for the circle, which should be the direction of the center line of the vessel. And we can get that. In this case, it's easy to compute, but if not, you can get it from the path object. So you can get the curve tangent at the curve point that's closest to your location. And then we just need to add each of these contours that we're generating to a list of contours. And then once we're done with that, we can generate a modeling polydata object, and we can set the surface of the polydata to be the surface that you get when you loft all of the contours. And you can set certain options for the lofting based on your preferences, but I generally just leave the defaults. And of course, you'll have to also pass in here your list of contours to loft. So once that's done, we'll have just a tube, and we need to cap the ends. So we'll just replace this surface with the capped surface, which we get by using this vmtk.cap function. And then after that, we use this compute boundary faces to separate out the different faces of our surface model. And then once we do that, we do some further logic to separate out what's a cap and what's a wall, because we'll need that in later parts of this when we decide how to save different surfaces. Okay, and once we've done that, we can write out this lofted cylinder solid model to a VTP and look at it in SimVascular also. So let's go ahead and run that. Let's find the terminal again. Here we go. Okay, so now I'll go up to this next breakpoint. And now you can see we've built this VTP here. So let's move that here. We don't need the path anymore. And sure enough, here's that lofted solid model. And we also see the caps. So that's good. Okay. So the last step that we're going to do is actually build a mesh that we can run a fluid simulation on. So we're going to create a TETGen meshing object and specify our model as the geometry that we are interested in meshing. And then you can go ahead and specify a set of TETGen meshing options. These are, again, the defaults, but of course you can change them for whatever you need to do. And then I've also included two kind of extra meshing features here. The first is a sphere refinement. So we might like to refine the mesh in the area around the stenosis so that we can better capture any more complex fluid dynamics that happen there. So in this case, we can use the sphere refinement feature, which refines the mesh inside of a sphere for which we specify a center and radius. So here I've specified radius 1, and I want the center of my sphere to be at 200, which is this second location where we have the narrowing. And then I can choose also the edge size that I want to have inside the sphere. And I've chosen that to be half the edge size that I'm prescribing everywhere else. And then another thing you may like to do is add a boundary layer for your fluid simulation. This is also really straightforward. Just prescribe whatever boundary layer options are right for your problem. I've chosen these. And then you'll also have to prescribe, of course, where the walls are. So the meshing algorithm knows which way to generate the boundary layer mesh. And once you're happy with all your meshing options, you can go ahead and generate your mesh like this. And then here I've just written some more commands to save basically the fluid mesh, the walls, the caps, and the full exterior, which are all models that you may need in setting up your fluid simulation. So let's go ahead and run this last part of the script. Okay. So now we see we've created all this extra stuff, and let's go ahead and look at some of it in SimVascular. Okay, so we've made this mesh complete folder, which contains all the mesh things. First off, we can look at the solid mesh. Sorry, the fluid mesh. This looks correct. We see the refinement here at the stenosis as well as the boundary layer. So that's looking good. We can look also at the walls. Oops. This also looks as expected with the caps not present. And then we can look at the caps individually. So here's one cap, and then the second cap. And you'll need to be able to isolate the cap to prescribe the caps to prescribe different inlet and outlet boundary conditions. So it's important to save those separately. And then finally, we have also a surface mesh that shows the complete exterior of our vessel. Okay, great. So that's everything I have to share today. But of course, there's lots more you can do with the SimVascular Python API. It's a great tool and definitely encourage all of you to try it out. Thanks.